Hello. Today we discuss the Roofline model. The Roofline model is a very convenient and popular way to illustrate and highlight how good a piece of code uses your machine. It also provides hints which type of optimization might pay off. We start from an extremely simple machine model, basically our vanilla von Neumann architecture. There is a compute unit hosting the ALU, system memory, and there is a bus in between. This machine runs through a piece of code one step after the other. Now let's zoom into the code and characterize it. Doing so requires that we restrict our focus on small code snippets one at a time. That can be a function or a single loop within our code. Each code snippet has a certain number of floating point operations to complete, and in order to complete them, it needs to load and store a certain number of bytes. The former is considered the useful work, our actual calculation, and the latter represents some memory movement associated with performing this work. Comparing the work per memory movement yields a useful quantity. Dividing the number of floating point operations by the number of bytes moved gives us something we call the arithmetic intensity. So, if a code does a great deal of floating point computation with a small amount of input data, then the arithmetic intensity is high. Likewise, if a code moves around a lot of data but does not compute anything, the arithmetic intensity will be rather low. If a code needs a lot of if statements and branch distinctions, that's fine, but these logical computations don't really contribute towards the outcome. They are overhead from a science point of view. This leaves us with the arithmetic intensity, which is simply one scalar that tells us how much useful work a piece of code does relative to the amount of data movement it requires. Now, when we run this simple code on a real machine, we measure a certain number of floating point operations or flops per second that are actually delivered. This quantity depends on many things, among them the actual machine character with its caches and vectorization, but also how many if statements we have in there and how we structure our code. So, we have the arithmetic intensity on the one hand, which is a measurement for the useful work per memory movement, and the measurement of the computations per second done in the real world. We can measure both quantities on a computer given the right tools. Let's use the two ingredients and plot them in a graph. In this picture, the x-axis is the arithmetic intensity and the y-axis is the megaflops per second. Each dot represents the arithmetic intensity and the floating point throughput for a function or an expensive loop within our code. We get a scatter plot characterizing the overall code. There are some parts with a very low arithmetic intensity, and there are some with a very high arithmetic intensity. And some of these correspond to a high computational throughput as well. If you want, we can make the dots of the functions that consume a lot of the actual compute time bigger or color them in, so we get an idea visually what the most expensive program parts are. This scatter plot gives us an overview how compute intense some code parts are versus what proportion of the actual compute efficiency they actually deliver. Now, let's add some information about our machine to the sketch. We know the frequency of our CPU and how many cycles the ALU needs for a single floating point operation. This gives us an upper bound for the maximum megaflops per second. We can draw this upper bound as a horizontal line in our Roofline plot. Naturally, no code part should give us more computations per second than this horizontal line. But wait, some dots here do. Why is that? Well, we have vectorization, and as we recall, vectorization boils down to the idea that we can do 2 or 4 or 8 operations for the cost of one single one. Therefore, we do not have one horizontal line, but we have multiple horizontal lines corresponding to different hardware utilization strategies. We have the lowest one for the scalar capability of the machine, and then we have one for SSE, which means the oldest type of vectorization, and then we have one for AVX, which means we can do 4 or even 8 operations at once, and we might have additional levels on top. The uppermost line is the maximum that the machine can deliver, full out, as optimized as anyone can manage. The lowest line is the upper bound for a code which does not vectorize, but does not waste any time in if statements or things like that. The corridors in between the lines are reserved for code parts that do some vectorization but struggle to exploit the whole machinery. We will dive into reasons for this later. Obviously, we want the dots to be as high up there as possible. We want to ship code where most functions make the best use of the underlying hardware possible. Unfortunately, we have natural enemies to achieve that. The one we've seen over and over again is the von Neumann bottleneck. We have to go through the bus to fetch data from main memory and again to deposit it there in return. This is slow. Let's think about this. If our code does one floating point operation for every 16 bytes it reads and stores, and if our memory can deliver 32 bytes every second, then you can do at most 2 floating point operations per second. Obviously, these quantities are totally out of scale, but the important thing here is the idea. What we describe is the best case scenario for memory-bound code. Now, if our code does 2 floating point operations for every 16 bytes it reads, we have doubled the arithmetic intensity. Likewise, we can also deliver twice the flops in the same time. If we add this threshold that arises to the graph, we get a diagonal line. Twice the arithmetic intensity means twice the throughput. Now we have 2 thresholds. We have one for the maximum number of computations per second, the horizontal lines, and a diagonal one which denotes what the maximum number of bytes are that the system can pipe through the bus. Once more, there are program parts which seem to process more data than the subsystem is able to deliver. And once more, this seems to be impossible. However, we have caches. Caches have a higher bandwidth than the main memory, that was the whole point of introducing them, and therefore yield a better diagonal line. We have only 1 cache here, while typical systems have 3, but the principle should be clear. It is time to clarify what we can read out from this Roofline model. Here, we have 1 function or code part which operates almost exclusively on data that resides already in the cache. We have 3 code sections which are solely constrained by how many bytes the memory can deliver per second. They are clearly memory bound. Then we have 1 routine that seems to make good use of SSE vectorization. Another one seems to be compute bound, but it seems to do solely scalar operations, that is, cannot exploit the vectorization capabilities. The most expensive code part here is neither compute bound nor memory bound. So what do we do with this insight? Obviously, we would like to move all dots as high up as possible. The first thing we should look into here is the dot that seems to be bound by scalar operations. We have to study this one and understand why no vectorization is used at all. Maybe it's an unfortunate way how we write down our code, or maybe we have used the wrong compile flags. The big dot in the center is the strange one. This one neither reads a lot of data, nor does deliver enough megaflops. That is one we have to just study in more detail. The 3 code fragments that sit on the memory bound line are tricky. Here, we could introduce vectorization, but it will not help us in any way. If the memory subsystem cannot deliver more data, the best vectorization is of no use. What we have to do is to increase the arithmetic intensity first, which corresponds to moving toward the right of the Roofline plot. Going far enough will increase the potential performance bound, and then we can think about the vectorization. There are various techniques to increase the arithmetic intensity of an implementation. A standard one is loop fusion. Assume that the 2 greenish dots represent a scaled vector addition. We compute alpha times x plus y. This is something we call a DXP. A naive version first takes x and then scales each entry with alpha. That data is then written back to main memory. That's the upper green point. And the second loop then reads this temporary result back into main memory, adds it to y and writes the result back. If we combine the two loops into one, we will get a higher arithmetic intensity as we skip the right read of the temporary result. We'll move the fused dot to the right, and then maybe we can see if vectorization pays off. As a summary, the Roofline model gives us a characterization of our program parts. If we consider small portions in which we can estimate the arithmetic intensity, then we can understand the performance data in terms of hardware the program is running on. We can extend the analysis to multi-core processors and build in all we know about our machine instruction sets and caches. Eventually, Roofline gives us a guideline what kind of optimization might be beneficial for a particular code part, and importantly also indicates which optimizations will not add any performance. The Roofline model is, at the moment, the best way to present that our code uses our machine efficiently. That's all on this model for the time being. It is time to apply these lessons learned into practice now. Thank you very much for watching, and I will see you in another lecture.